All right, so first things first, we want to do a division to get it into a hyperbolic form. So if we do our 2x plus 3 goes into, rearrange it, negative 2x plus 3. So negative 1 times 2x will give you negative 2x, negative 1 times 3 is negative 3. Just be careful with your subtraction. 3 minus 3 is positive 6. So it goes negative 1 times plus 6 remainder over 2x plus 3. So then we have to be careful and state the values of A, B, and D. So A is negative 1, B is 6, and my domain, specifically stated, well, 2x plus 3 can't be 0, so x can't be negative 3 on 2. So you're going to need all of those 3 bits of information, and undo that. I did end up marking this one out of 2. All right, so then we need to sketch the graph. So hopefully we realise that our graph has been shifted minus 1 unit down. So 1 unit down to y equals negative 1. My vertical asymptote at x equal to negative 3 on 2. Quick little check, I put x equal to 0. I think here is just as easy. If I put x equal to 0, I end up with 3 on 3, which is a 0.01. And then if I put y equal to 0, you can see I can rearrange that equation. I guess the thing to remember is if y is equal to 0 and we've got a fraction, the denominator can never be 0. So the only way a fraction can be 0 is if the numerator is 0. So 3 minus 2x has to be 0. So x is equal to 3 on 2. So make sure we label coordinates, asymptotes with equations, and it is a good practice that I don't always do, just to pick another point, just to give you an idea of the dilation factor. You know, how steep should your graph be? So I just randomly picked x equal to negative 3 because I got a nice answer. So the graph goes through the point negative 3, 3, negative 3, negative 3 to just give you an idea. Find the inverse function, swap x and y. It's easiest to use the functional form. Take the 1 across. So from this point here, I guess in reality, you're sort of multiplying 2y plus 3 across to the left-hand side, but then bringing x plus 1 back to the right-hand side. So in reality, we're just swapping those expressions or flipping one upside down. So then I'm going to end up with my 2y plus 3 is equal to 6 over x plus 1. Take my 3 across, then divide my 2 over. Yeah, so the 2's going here, and that 2 and that 6 cancel to give me the 3. And then I've also got 2 goes into negative 3, which is a negative 3 on 2. So there's the rule. My function, f inverse of x, is equal to 3 over x plus 1 minus 3 on 2. Don't forget to put the f of minus x. State the domain. Well, the domain of the inverse is the range of the original. And you can see very clearly the range of the graph above there is r except for negative 1. All right. So continued on. Show that f inverse of f of x. So I've got to substitute f of x into the inverse. All right. So you can see in black I've got the f inverse, and in blue I've got f of x. So if I do that, that negative 1 and that positive 1 cancel to give me a 0. So I get 3 over 6 over 2x plus 3. So if I divide by a fraction, I flip upside down and multiply. So I get 3 times 2x plus 3 over 6. Cancel a few things there. I get 2x plus 3 over 2. So divide that 2 in. X becomes a 1x. I get 3 on 2 minus 3 on 2. And we very quickly come down to x, which we should know. It wouldn't matter if I then put f of f inverse of x. That's also x. All right, let's move on to question 2. We've got a quadratic. Largest possible A B such that it's a one-to-one function. So any quadratic is going to be one-to-one either side of the axis of symmetry or the vertex, yeah? So I need to find that turning point. So I can find the turning point by negative b on 2a, or I complete the square. Completing the square is really the way we need to go because we need that form of the graph to help us find the inverse. So if I complete the square, let's take that negative sign out the front. So I get x squared plus 4x minus 5. Negative sign, big square bracket, halve the middle term and square it, yeah? So we get x plus 2 all squared, plus 4 minus 4, and then minus 5. So I end up with the negative outside, if you like, and that expression there is minus 9. Multiply that negative through, and there's my vertex. So it's a turning point of -2, +9, okay, but it's an upside down parabola. So given the turning point is at -2, my graph, -2, +9, a quick check, if I put x equals 0, it's 5, so it looks a little bit like that. Yeah, so that's the point there, that it stops being 1-to-1. So since the domain has been restricted from -infinity to b, b has to be -2, all right? So once I've got that, I'm looking to find the inverse function, which means the easiest way is to start with my turning point form. I've only got one representation of x. So I just have to swap the x and the y, bring the 9 across to -9, bring the negative sign over to make the x negative and the 9 positive. Then I take a square root. Bloody common mistake. We're not taking the plus or minus. Every time you square root a function, you're getting a plus or a minus. So then if I take my 2 across, there's an equation there. All right, now, whether I take the plus or the minus is really determined by the domain of my original function. So since the domain of the original function was -infinity to 9, that's the range of my new function, or my inverse function. So my range has got to come up with some really big negative numbers to fit in here, which means I'm going to take the negative component. Yeah? So -2 minus square root of 9 minus x. I write it as f inverse of x, don't leave it as y. So there's my inverse function. And then sort of straight from the information discussions we've had, the domain of f becomes the range of the inverse and vice versa. Okay. Finally, question 3, a messy question, but you know, I guess there's a few things in there. I think for those of us that like to find where our equations are parallel or the same by comparing gradients, this question became a little bit trickier. So from the equation 1, what would y equal? Y would equal 3x minus 5 on k squared. And the other equation becomes, y is equal to 5k minus k squared minus 10x on 8. So I guess we're comparing 3 on k squared has to be the same as negative k squared minus 10 on 8. And then if we cross multiply and rearrange our equations, we end up with exactly this by using the determinant, okay? So 3 times 8, bracket, minus, bracket, negative k squared times k squared minus 10. Expand and group terms, I end up with k to the 4 minus 10k squared plus 24 equal to 0. So we've got to notice that that's actually a quadratic expression. All right, so if I put u equal to k squared, u squared is k to the 4. So u squared minus 10u plus 24 is an equivalent expression. All right, and if I factorize that, I get minus 6 minus 4. So u is equal to 6 and u is equal to 4. Substitute my k squared in. I get k is equal to plus or minus root 6 plus or minus 2. So what that tells me is that at plus or minus root 6 or plus or minus 2, my equations, my lines are either parallel or the same line, okay? Which means for every other k value, I get a unique solution. So that's the significance of those values there that make the determinant 0. So my unique solution is everything except for the values that I come up with, all right? Now the next part of it is, okay, for those values you've come up with, which of those will give you infinite lines or infinite solutions or no solution? So we have to check. So if I consider the plus or minus root 6 together, just be aware of it though, and substitute it into my rule, I'm going to end up with, go back to yellow, I'm going to end up with 3x, root 6 squared is 6. Well, plus or minus root 6 is positive. So I get 3x minus 6y is equal to 5, which means y is equal to 3x minus 5 on 6. If I put my root 6 in to the equation B, again, I'm going to get 6 minus 10, which is negative 4, plus 8y equals plus or minus 5 root 6, just depending on whether they have a plus or a minus. And if we look, y is then equal to a plus or minus 5 root 6 plus 4x on 8. Consider the gradients. I've got 3 on 6 and 4 on 8, so both gradients are a half. So they're parallel lines. And because plus or minus 5 root 6 is different to negative 5, it doesn't matter whether it's a plus or a minus, they're going to be parallel lines. So for plus or minus root 6, we've got the same gradient but different constants. So parallel lines, so no solution. So I've got to go through and do the same thing now for plus or minus 2. So again, if I put the plus or minus 2 in, it has no impact on the first equation, 3x minus 5 on 4. And in the second equation, I'm going to get y is equal to 6x plus or minus 10, depending upon whether we have positive 2 or negative 2 on 8. Again, note that the gradient's the same, so that's a good sign. And that the y-intercept on the first one is negative 5 on 4, which if k is negative 2, it's the same y-intercept on the second one, also negative 5 on 4, which is 10 on 8. So if k is equal to negative 2, the two lines are going to be the same. Otherwise, they'll be different. So that's the final piece of the puzzle. So if we summarise that, my unique solutions can be anything you like, k, except for plus or minus 2 plus or minus root 6. And if it is plus or minus 2 or plus or minus root 6, negative 2 will give you the same line, so infinite solutions. And 2 and plus or minus root 6 will give you parallel lines, so no solution. All right, so you just got to try to come up with a nice formal process, just a regular routine to solve those questions. Okay, so we've got a cubic graph here. All right, so there's my cubic, and we note that my intercepts are at C, which is a stationary point, and at A. Note A is in fact positive. It represents a negative value because it's on the left-hand side of my axis, but the pronumeral we're using is positive A, which means my intercepts, or the rule could be written as x minus A, x minus C all squared, which as linear factors are x minus A, x minus C, x minus C. Remember, we refer to x minus C all squared as a repeated linear factor, which means it's a turning point. All right, so just linear factors, coefficient of x, the degree on x is 1. All right, whereabouts is this particular function greater than 0? So it's greater than 0 everywhere where it's above the axis. Above the axis, which means at C where it's on the axis and at A where it's on the axis, it's not greater than 0, it is 0. So that sort of summarises. We can go from A to C, not inclusive, and then from C to positive infinity. All right, state the values of P in terms of A and B, or C, such that f of x equal to P has only 2 solutions. So by 2 solutions, we're saying there's only 2 points of intersection. So when f of x is equal to, say 3, if f of x is equal to 3 or it's equal to negative 1, how many times do the lines intersect? Well, from the dotted lines above, hopefully we can see that at that point there where the intercept is, the turning point, and a corresponding point on the axis, 2 points of intersection. If I come down lower, I'm going to have 3 points of intersection. No good to me. The other point is on the axis. We're at A and at C where they both touch, 2 points of intersection. If I come down too low, only one point of intersection. So I've got two specific lines, okay? So at the point B, so at P equal to B, f of x equal to that value B, there'll only be 2 points where they touch, and at x equal to 0, P equal to 0, again, there's only 2 points of intersection. So I must confess the two answers I was looking for was P is equal to B and P equal to 0. But as suggested to me, because P equal to 0 can't be written in terms of A, B, or C, I guess you could argue, we could argue that P is equal to 0B or 0A or something. If that was your reasoning for not accepting or for not putting in 0, that's fine. If you just forgot it, that's not fine. But really, P equal to 0, P equal to B are the two solutions I was looking for. The final one, which I'm not looking forward to explaining, is, okay, so we've got the graph of f of x minus h, only has one positive solution, f of x minus h equal to 0. So in other words, solve f of x equal to 0 is the same as finding your x-intercepts. So in other words, only one positive x-intercept. So if you have a look at the graphs at the moment, you've got A and C, and there's one positive and one negative. So I can move my graph a certain distance to the right and keep only one positive solution. If I go too far, it'll become two positive solutions. So in other words, if I go to this, okay, I end up with two positive solutions, which is no good. All right. So how far to the right can I move the graph? All right, so we're talking to the right. So f of x minus a will move the graph a units right. And if I go a units right, that'll move that intercept to the point 0, 0. So I can move it a units right. Let's think about number of units left. If I go c units to the left and put that at 0, 0, I'll have no positive intercepts. I'll just have a 0 intercept, neutral, and a negative intercept. So I can't shift c units left. So now the next discussion is, okay, how do I move left and right? So I need f of x plus c will shift the graph c units left. And to get f of x plus c out of f of x minus h, h will have to equal negative c. But it has to be less than negative c. It can't be any more than that. So I need h has to be, greater than negative c, because I don't want it to move. So think about it. So if c is negative 4 or negative 5, that would move it 4 or 5 units to the right, which is too big. So I need h to be greater than negative c. What about the f of x minus a? How do I go a units to the right? Well, to go to the right a units, I need f of x minus a. Yeah? That makes it a units right. But a itself is a negative number. So, in this case, f of x plus a, okay, where a could be negative 1, negative 2, negative 3, will move the graph to the right. Because I know a is less than 0. So normally f of x plus a moves to the left. So that moves to the right since a is less than 0, since a is a negative number. So if I need f of x plus a and my function is f of x minus h, well then h has to be equal to negative a. So what about negative a? It can be negative a, because if it is negative a, it'll be at 0, 0. So that's what I'm looking for. Okay, get a bit more routine. We've got our transformation matrix, so x dash is equal to 2x plus 1, y dash is equal to 4y minus 3. The key is to remember, we're looking to get our new equation. So I want to substitute these values into y equals 1 on x. So I've got to have y equals and x equals. So rearrange, x will be equal x dash minus 1 on 2, y will be equal y dash plus 3 on 4. Now I can substitute them into y equals 1 on x. So if I do that, I think it's easiest to tidy up the right-hand side first, divide by a fraction, flip it upside down and multiply. So I get to there. This 4 in the denominator has to multiply across to make that 8. Then I subtract 3. So there's my new rule, but I have to state the values of A, B, and C. So A is 8, B is -1, and C is -3. Okay, so the multiple choice function has a maximal domain. A possible rule for F is, so there's just got to go through a list of domains. Obviously, we may not be fully aware of what the log function domain is, but if you go through, you can see very quickly, this one here can't have -1 because it will give me a 1 on 0. So very quickly it becomes obvious that it's D. All right. My composite functions state the information you're trying to prove. So for f of g of x, the range of g is a subset of the domain of f, which means I need the range of g to be a subset from 0 to infinity. So my g graph needs to have a range of 0 to infinity, which is this section. Yeah. So that's a range of 0 to infinity. So how do I get that? Well, I restrict the domain to be from -1 to infinity, which is B. 3 was another interesting one. So if we think of how can we transform P to Q? Well, there's just two possible scenarios. I can add 2 to x and multiply y by 3. I could possibly multiply the x value by 3 and subtract 4 from the y value. So there's going to be a range of different possibilities. So I think the easiest way is maybe pick one or two, pick one of them and get a feel for what's happening. So if I go to the first one, all right, so if I bring the 3 across, I get 3y dash is equal to f of x dash plus 2, because they're my new functions, all right? So again, just do my little y equals 3y dash, x is equal to x dash plus 2, rearrange to get y dash equals and x dash equals. So what I'm saying is x dash y dash is equal to x minus 2 1/3 of y. So if that's the case, the point 3 -6, which is my new point, would have to equal my old point 1, 2, 1 minus 2, and the third times -2, which it doesn't work. So looking at what we've done here, we can see that instead of multiplying that y coordinate by a third, I need to multiply it by 3. So maybe instead of having a third out the front, I should look at having a 3 out the front. And that x plus 2 on the inside subtracted 2 from my x coordinate. So what if I make it a -2? And that way I could add 2. So I could get a 1 plus 2 and a 3 times -2, which fits. So if I check C, do exactly the same thing, except I have a 1/3 y dash out the front for y, rearrange to get y dash equals and x dash equals. I get x dash is x plus 2, y dash is 3y, substitute my point 1, -2 in, and I get the point 3, -6 that I'm looking for. So I think, which makes it C. So I think it's not a bad way. Just check one of them and just see what impact each of these things are having. And you should be able to intuit as well. We know that x plus 2, translate our graph 2 units to the left. So we're subtracting 2 units. So, we should be able to intuit that we probably do need a -2 in the bracket. So we're adding 2 units by moving to the right. And 3 at the front of the function is a dilation from the x-axis, which multiplies my y value by 3. So you may not need to go as formal as that, but that is certainly one way. When will it have an inverse function? So sketch the graph. You've got a CAS, sketch the graph, and I've got my key turning points are at -1 and +1. So that section there is 1 to 1. That section there is 1 to 1. That section there is also 1 to 1. So I just need a domain that describes any one of those sections. And from -1 to 0, which is that section there, my graph is 1 to 1. So B is the correct response. Functions here have maximal domains if g of x equals root x and g of f of x could exist if. So they're both, so again, I need the range of f to be a subset of the domain of g. So which of my functions here listed have a range from 0 to infinity or inside of that? So all of these have got ranges of R, so they wouldn't fit in, they would have to be restricted. D has got a range from 1 to infinity. And E has got a range from 0 to infinity. I'll just pause that because that should be a negative one there, shouldn't it? I was wondering why D didn't fit in. So the only one of these functions that has a domain that fits in is E, which has a domain from 0 to infinity. All right. Okay, again, it might be just a little bit of substitution. F of x squared, what is f of x squared in each of these functions? It's x squared plus 1. It's 1 on x. It's either the x squared on 2, 1 over x squared minus 2, and then the natural log of x squared. So you're trying to compare, will any of these possibly be the same as 2 times f of x? And clearly the first couple aren't. It's the log one, and again, it's probably a little bit outside at the moment, but you can check on your CAS. That 2 comes out the front, doesn't it, and becomes 2 natural log of x, which is 2 times f of x. So E is the one there, but again, maybe a fraction early for that. The domain and range of f of g of x respectively are. So for f of g of x, the domain of f of g is the same as the domain of g. The domain of g we've been given is from -infinity to 0, so that makes it A, B, A or B. The range of f of g of x is just the range of the function. So I've got basically the square root of some function in there. And typically, this domain is from 0 to infinity. Is there any reason why it shouldn't be that or wouldn't be that? And the answer is no. Because I'm going to put the values from 0 to infinity into that function, x squared minus 2x. And that's going to generate values from 0, where x is 0, up to really big positive numbers, and we get really, really big. So B is the answer. Question 8, another tricky-ish sort of one. Again, do a diagram. So I reckon already 3 times I've said do a diagram, okay, whether it's with your CAS. So if I just do a quick graph sketch of 1 over x minus a plus b, I know it's shifted a units to the right and b units up. And those red lines represent roughly where the functions are. The key is to identify the domain of the function. So the left limit at -a, the right limit at positive 2a. So if I substitute those points in, so for example, if I work out g of -a, I get 1 over minus a plus b, which is equal to b minus 1 on 2a. And then if I put g of 2a in, I get 1 over 2a minus a plus b, which is equal to b plus 1 on a. So they're my endpoints, because that's the end of the domain. So from the right-hand side, as I go to the left, well, my function gets as low as 1 on a plus b, but it goes up to positive infinity. So it goes from b plus 1 on a up to positive infinity. And on the left-hand side, it goes down to negative infinity and up to b on 1 minus 2a. The decision you have to make is round bracket or square bracket. And given our domains, the endpoints are both square brackets, we're going to go for option E. Question 9, another tricky one. Again, do a graph. So we know that the graph of a cubic function has a minimum turning point at the point 1, 0. At the point 1, 0. So This isn't the version I wanted. You can see I've made a little mistake here, but I can fix that as we go. So if we have a look at some possible graphs here, so let's consider the first one. I'll leave that pencil on. It says that the cubic has a minimum turning point at 1, 0. So this could be version 1 of the graph, and down here is version 2. So there's a turning point defined only for x is greater than 0. So what about the transformations that have taken place? We've got x dash is equal to 2x plus 1 and y dash is equal to negative y. So I've multiplied the x value by 2 and add 1. So this turning point now gets multiplied by 2 and I add 1. So it comes over here to the point 3, 0. This stationary point moves across to somewhere less than 3, okay? And then we reflected it upside down because of the y equals negative y. So this minimum turning point became a maximum, and this minimum now is somewhere between 0 and 3, all right? Or graph 2, again, we haven't got the first part of the graph, so I've got a minimum at 1, 0, and then it continues down. Again, I multiply the x value by 2 and add 1, so it becomes 3, 0. Then I flip it upside down, and it becomes this graph, where I've got a maximum at 3, 0, and a minimum somewhere greater than 3. So we're referencing the minimum. So the first possibility has a minimum somewhere less than 3. The second one has a minimum somewhere greater than 3. So will it have a minimum where x is less than negative 2? Well, clearly not. Between 0 and 1, I don't think we can agree to that. No, well, each of the values are going to be multiplied by 2, but then 1 is being added to it. So whatever that is, I'm adding 1 to it. So that point here is greater than 1 because I'm adding 1. Less than 1 for the same reason, no. What about at x equal to 3? Well, at x equal to 3, all I've got, I've got a maximum at x equal to 3. And again, a maximum at x equal to 3. What about the minimum at x greater than 3, which is this one here? So that ticks off. So E is the only one that really ticks the box. So again, if we have a diagram can help represent, and it's just thinking about the possible scenarios. All right. Finally, 10, the remainder theorem. So if we substitute 3 into P of X, it'll give us the remainder. And in this case, we're told the remainder is 15. So P of 3 has to equal 15. And if we evaluate all of that, we get B, which is 2. All right, so what have we got here? So we've got a transformation, and we've got to transform this graph into y equals root x. In other words, I'm going to move that to the right 1 unit and up 1 unit. So I've got to add 1 to the x and 1 to the y. So to do that, the c value has to equal 1 and the d value has to equal 1. I think that's the easiest way to think it through. What about for the second one? The point negative 2, 1. The point negative 1, 1 has to end up at the point negative 2, 1. So how does that happen? And looking at x dashed is equal to ax, isn't it? And y dash is equal to by. So we're talking about dilations. So the x value has to be 2 times the current one. So we're going to multiply by 2, and the y values don't have to change. So that means the a value, if I want to affect the x coordinate, I've got to multiply it by 2. So a value is 2 and b value is 1. Keeping that in mind, find the values of n for which h of x. So what does that graph look like? So we've just sketched it minus n and something like that, doesn't it? Minus n. So whereabouts is that function greater than 0? So I need the graph, which has been moved down to there, I want that value there to be 0 or negative because I want to do a minus minus. Yeah, so I want to move my graph up to here somewhere. So that graph there, the end value has to be negative, any negative value, because it'll be minus a minus, which makes a plus, or 0. So n has got to be negative infinity to 0. Find the rule for the inverse. Again, swap x and y, square things, which is different to taking the square root. So y is equal to x plus n squared minus n. So h inverse is x plus n all squared minus n. So there's my rule. State the domain. So the domain for that function is determined by the range of the original. And this range is from negative n to infinity. Find the coordinates of the points of intersection. So really we're solving exactly that. The points of intersection, don't forget, between h and h inverse are on the line y equals x. So x plus n all squared minus n is equal to x. If I solve that on my CAS, I get 2 points at negative n and 1 on n. So my coordinates are exactly that, negative n, and 1 minus n, 1 minus n, okay? All right, consider the function. So I mentioned in class, this function is actually find the values a, b, m, and n. So a couple of things we can work through here. If we consider the function y, the transformed function y is equal to k over x plus k from the original function y equals 1 on x. So I get this function y equals k over x plus k into the same form as y equals 1 on x, okay? So there's that relationship. The second one, let's multiply out our transformation matrix. X dash is equal to ax plus m, y dash is equal to by plus n. So x dash minus m on a is equal to x, y dash minus n on b is equal to y. So we get our values. If we substitute that into my original function, y equals 1 on x, I get y dash minus n on b is equal to 1 over x dash minus m on a, which is the same as y dash minus n on b equal to a over x dash minus m. That, okay, needs to be the same as, I'll use blue. That's my new function. That's the function I wanted to end up to be. And this is the function, the transformation is that I get if I apply the transformation. So that means then that what we're saying is that y dash minus n on b has to equal y dash on k. A over x dash minus m has to equal 1 over x dash plus k. So if we equate everything here, the b value has to be k. That n value there must be 0, so come up to the top. The a value here is going to be 1. And what have we got down here? The k value there is equal to negative m, or m is equal to negative k. All right, so it's a little bit complicated or confusing because there's no numbers there. So you've just got to try to remember to follow your process as you normally would. And if it was an exam and it's a trial paper question, just put some values in for A and B and just see how your process will pan out. A to B either from negative infinity. Then we need to find the inverse of G, find G inverse, the inverse of the function. So if X, we swap X and Y. So X will be equal to K over, it's Y plus K. So multiply that across, bring the X back. So I get 1 on X is equal to Y plus K on K, multiply K, subtract K. I get Y equals, and then we'll make it G inverse. That's a G inverse there, equals K on X minus K. Finally, The point with coordinate QCC lies on the graph of both functions. So again, where do my points of intersection occur between the inverse and the function? So I want to solve the function equal to y equals x. Use my CAS for that. And well, I didn't, but I would use my CAS for that. I get quadratic formula here, and I get that expression there. So that's the point of intersection. So C is equal to negative K plus K times K plus 4 on 2, or negative K minus K times K plus 4 on 2. So there's 2 points of intersection. So what conditions on K? Well, we know that whenever we have a square root sign, whatever's in the square root sign has to be greater than or equal to 0. And for that to happen, to -4 or from 0 to infinity. Righto.